All right, guys. Good afternoon. Monday, week 4, and of course, you're receiving a video of mine. You have already received feedback, individual feedback about your LOs. Concerning the first LO with the bones, nothing really from me to explain. On average, very well. Some mistakes that I saw, it's not it's not that most of you missed a specific item. The ones that you have missed, the answers are in the book. Nothing too fancy about that. The second one that had 3 scenarios and you had to pick one case study. I don't really know why 1/3 of you picked all 3 of them. I don't know if you're watching these videos. I hope you are. Hopefully it's not that you're watching them and you can understand my accent. But in any case, at any point, if you have questions, if you're not sure about what to do, if I send you mixed signals about something, like I write something different and I haven't given you enough information about that, or something that troubles you, confuses you, email me. Or tomorrow, like every Tuesday, for 4.5 hours, we have all. So log in, let's talk, okay? Yeah, I gave specific feedback about the one with the case studies, and I'm gonna share my screen now. Let's look. Let's go to our Moodle site and see what we have for where we are and what we have for next week. All right, PED212, excellent. So week 4, which means I'm gonna present chapter 5. I wanted to start it last week, but there was no reason, so I changed my plans. I'm gonna do the whole thing today. So a lot of information hang in there. And you have 2 LOs, LO7. Let's look at it. I'll give you some specifics. Kevin has already emailed me. I was about to explain this. You see there's a hard diagram PDF. If you don't have the software to edit and write on the PDF, that's fine. You can take a picture, print it, write it on it, take a picture with your phone, upload it. You can just take a Word document and write 1, 2, 3, 4. It's just the heart. And I want you to identify those different sides of the heart, parts of the heart, and just let me know. Okay, that's it. Everything is in the book, in our textbook. That's LO7, due on Sunday at midnight. Let's check LO8. So this is about the muscular system. We're going to go over more than one systems today. So A, in no more than 2 paragraphs. A, describe. B, compare and contrast. So you one paragraph, I would suggest 2, describe type 1 and type 2 muscle fibers, and another paragraph to compare and contrast. This is this, and this is that. Type 1, we usually use them during this, type 2 during that. They're similar to this, they're different when we see them in regards to that, okay? And use examples. For that event, most likely we'll use type this. For that sport, most likely we'll use type that. Just give me something. Activity, movement, anything. And then we have B. So B is different. That's another thing. So when maximal force is required, which motor units are activated? No more than 1 paragraph. So overall, no more than 3 paragraphs. And I have, you see that it's bold italics and units are activated. The answer is, guess where? In the textbook. And most likely, I'm going to give you enough hints today. All right? Those are the two things you have for Sunday. I'm going to stop sharing this. And I'm going to go really quickly to our slideshow because we have a lot to cover. So take your time and try to absorb as much information as possible. Try not to do it all at once. There's a lot going on. Exercise physiology is one subdiscipline of exercise science. And, you know, at least we could just have, and we do, one whole course about just X phase. All right, let me share my screen and let's start. All right, let's see if my clicker works. Excellent. All right, exercise physiology, chapter 5. We're going to talk about a lot of systems. We're going to talk about how they interact. And we're going to talk about energy metabolism. And we're going to cover a lot of information. In general, when we talk about exercise physiology, as I said, it's a subdiscipline of exercise science. We study how our body responds to a stress. With stress, the stress of exercise. Exercise is a stress. Is stress a bad thing? Not necessarily. Not necessarily. We'll cover that in other courses. It depends on a lot of things. But it's good to take our body on average, or most of the time, or under specific conditions, if it's safe and effective, our body through some stress, so we can adapt. Okay. Now, as you're going through that stress, which can be stretching my hamstrings later on, I will have some acute effects, like right after that. And if I keep doing it, some chronic effects. Okay. So we're going to talk about a lot of systems today, and we're going to see them from the acute effect side and then from the chronic effect side. Don't forget, although we're going to talk about them separately, those systems interact, they cooperate in order for our body to adapt, but before even adapt, respond to that stress. Okay. Let's start with the cardiovascular system. Okay. So when we talk about the cardiovascular system, we mainly talk about the heart and the blood vessels, and it's a closed circuit, which means the blood, for example, will start from point A, we'll do the whole thing and come back to point A. All right, so it's just closed circuit. That's an easy, simple way to try to explain that. We have nutrients that have to be delivered, and we have metabolic byproducts that have to be removed. The two basic things that happen, right? Also, you can see maintenance of normal function at rest and during exercise, and of course, all these systems are trying to bring us back to homeostasis, which is our equilibrium, okay? Our optimal condition when we are at rest. Okay, so what does the cardiovascular system do? As you can see, we have oxygenated blood, deoxygenated blood. The deoxygenated blood goes from the lungs, and then the oxygenated blood goes from the lungs to the heart. That alone is called pulmonary circulation or coronary circulation. And then we have oxygenated blood from the heart to the tissues, and then deoxygenated blood the other way around, and that will be the systemic circulation. So two types of circulation. What are we distributing? A lot of nutrients to the cells, and then we bring back byproducts of the metabolism from the periphery, so we can get rid of them pretty much. Also, as you can see, the cardiovascular system regulates pH. So if we have an excess of acid below 7.35, we have acidosis. We have an excess of base, which is above 7.45 of in our pH. We have alkalosis. Again, we're trying to avoid both of those conditions, and we want our pH to be regulated. Hormones and enzymes, very important, of course, regulate function, many function, many chemical reactions. Dehydration can be prevented, body temperature can be maintained. And now we'll spend some time here, and this has to do a little bit with your first LO. In general, first of all, you can see that we have pericardium here, okay, epi right here, endo right here. So peri, epi, endo as layers of the heart, and the myocardium again is it's strong muscle, as a muscle of the heart, as we call it. All this, all right. Now I'm going to try to explain a little bit what's going on with the heart. Okay, let's start with the deoxygenated or unoxygenated blood. That will come towards the heart from the periphery. Okay, it will come from the superior and inferior vena cava. So it will come in and will go where? Before I even start, I want you to understand and just try to see the heart as 4 chambers. We have the left side and the right side. The left side has 2 chambers, the right side has 2 chambers as well. The upper chambers are going to be called atria, so atrium, right? And the lower one, ventricles. So here, the blood is coming to the first chamber of the right side, the upper chamber of the right side, which is called right atrium. So we'll come in here, and here we find a valve, tricuspid valve. What do valves do? A lot of things. Mainly, they prevent backflow. Okay, so this is closed now, and the blood is coming in here. Now from there, this will open, and the blood will go where? To the lower chamber of the right side of the heart, which is called right ventricle. So we'll go in here. This is closing, so we don't have backflow. So the blood is here. From there, it will come here and will go out. It will go out. We'll have another valve right here. How is that called? Pulmonary valve. Okay, so the blood is going to come out and it's going to go from the left and the right pulmonary arteries to where? To our lungs. This, the pulmonary valve, will close to prevent backflow. It's going to our lungs to do what? To become oxygenated. All right. So when it's ready and it's oxygenated, it's going to happen what? It's going to come back to our heart through the pulmonary veins. And it's going to go where? It's going to go to the upper left chamber of the heart, which is called left atrium. Again, from the left atrium, we'll go to the lower left chamber of the heart, which is called, atrium will go to the ventricle. This valve will close, mitral valve, to prevent backflow. And from here, which is the left ventricle again, it will go out to the rest of the body so we can have that oxygen that it has in it, right? And here you see the aortic valve that it will close once the blood goes out. And you can see that from this side, it will go to our hands and brain. And from this side, the descending aorta, it will go to the rest of our body. That's it. Here, out to the lungs. And then from here, and we'll come back in from the lungs here, and then we'll go down here, and then we'll go to the rest of the body. That's it. 4 chambers, and I want you to know the exact circulation, the exact path of the circulation of the blood. Unoxygenated or deoxygenated and oxygenated blood. I hope you're clear. Rewind, go back, watch this again, read the textbook. I want you to know that. That's pretty basic. All right. Talk about that. We'll talk about that. All right. Yes, yes, and yes. We talked about the circulation, the circuits right here. One thing I want you to understand is that the heart, that whole thing, is going to be initiated by the nervous system. There's going to be some kind of impulse. That's how we have the first contraction, which happens at the SA node, which is called the intrinsic pacemaker, which is actually, when I took the test forever ago, that was a question in the ACSM CPT exam. Okay, so it starts from here, and then gradually we have the whole movement happening. Okay. All right. The blood vessels. So the blood vessels, what do? They deliver blood to the tissues. And we talked about exchange of nutrients and metabolic waste and more. Okay. Also, they're carrying blood to the heart, and we talked about this. So we have a closed system that's happening here, and you can see now that as we move this way, they become small. So from the arteries, we go to the arterioles and then the capillaries. And from the capillaries, they become bigger now, the veins and then the veins. This is very important because this is where all the magic happens. This is where we exchange the nutrients. This is where we take all this metabolic waste to bring it back and to get rid of it. So this is breaking down into this and this is becoming, as it's becoming bigger, it's becoming venules and then veins. So in a way, this kind of is the same as this, and then this is where both of these paths come together. This is where all the exchanges happen. I'm trying just to simplify it as much as I can. All right. Now it's good. Okay, we're going to go into some terminology today. Not too much, but hang in there. Heart rate. What is the heart rate? Is how many beats per minute. Okay, yeah. Average resting heart rate. Age at rest is between 60 and 80. It's higher in women. It's higher in adults. It's lower in the elderly, older adults, and also it's lower in fit individuals. Why? Because their heart is more efficient, so it doesn't need to work as much in order to move the same amount of blood. Okay, that's what's happening in fit individuals. Now, blood pressure. What's blood pressure? Keyword: arteries. Okay, so here, the systolic pressure, we have the pressure exerted on the arterial wall during contraction, and the diastolic pressure during relaxation phase of ventricles. Now, you see we have two numbers. We'll have SBP, DBP. SBP is always the higher number. Below 120 and below 80, that's normal. We're not going to go into detail today. There's something called prehypertension, and then above 140, 140 and above, 90 and above, we have hypertension. Is that a thing? Oh, yeah. Hypertension is a thing, and it's dangerous. It's called the silent killer. It's not a good thing at all. But we're just going to stop here. Okay, nothing more about blood pressure. Stroke volume. What's the stroke volume? The stroke volume is the amount of blood ejected from the left ventricle. We talked about the left ventricle in a single contraction. Okay, so we have the end diastolic volume and the end systolic volume. Diastolic, again, is when the heart, enlarges, and systolic is when it contracts and pushes the blood out. Now, the difference of these two is the SV. That's all I want you to know. And then we have cardiac output, Q. Q equals is the product of heart rate, which is the beats per minute, times the stroke volume, which is how much blood, the amount of blood is coming out of the heart in a single contraction. So we'll multiply this, which is the amount of blood in a single contraction, by the amount of contractions per minute, you get the amount of blood you push out of your heart per minute. Okay? Cardiac output, sensitive to body position, stroke volume, also sensitive to body position. Acute responses. What's acute? Acute is a short term, right after we do something. And in this case, we talk about cardiovascular exercise, cardio, aerobic. Okay? As exercise intensity increases, oxygen consumption will increase, of course, and carbon dioxide production will also increase. I think that's pretty easy to grasp. Now, in any case, all systems, including cardiovascular system, is trying to maintain cellular homeostasis. So at the cellular level, to be in an equilibrium. Okay, so after whatever you do, your body is so amazing, it's trying to bring you back to the state you were at rest. Make sense? So in order to do that, one way to do that is the CNS, the central nervous system that we're going to talk about more in a little bit, increases the neural ventilatory, right, and cardiac drive. That's a way, by doing that, right, our body is responding. That's a short-term response, acute responses to some kind of aerobic cardiovascular, let me say cardiovascular, not aerobic, activity. Okay, and by doing that, our goal is cellular homeostasis, bring us back to an equilibrium, to the equilibrium at the cellular level. All right. Excuse me. Let's break it down a little bit more. Heart rate. Heart rate will increase linearly. Okay, which means the work rate, as the work rate increases, you'll see an increase in the oxygen uptake, which is would be like a straight line if you had a diagram. Okay. Now, how can we find the HR max, which is a maximum attainable heart rate? There are a lot of ways to do it. We're going to talk about that in other chapters. A very generic way to do it that is kind of off anyway, but we use it a lot, is you take 220 and you subtract your age. So if you are 20 years old, what's your HR max? It would be 220 minus 20. So your HR max would be 200 beats per minute. Cool? Okay. Now, stroke volume. What happens to stroke volume? Stroke volume increases curvilinearly. So it's not linear. So up to a point, you'll see it increases a lot, and that's 40% or 50% of your aerobic capacity, maximum aerobic capacity, and then it stops. It can't increase anymore. You can't increase the amount of blood you're pushing out of your heart every time it contracts forever. So that increases up to 50% of your maximum aerobic capacity. Okay? Now, if we still need to increase Q, which is the cardiac output, what's Q? Q equals SV times HR, right? That's the product. So if we still need to increase Q, since SV cannot increase anymore above 50% of our aerobic capacity, what do you think will increase? Exactly, the heart rate, HR. Okay, that's how it happens. All right. That's how it happens, and of course depends on many factors. Nothing too fancy here. I just explained that. Okay, now here we have the arteriovenous oxygen difference, and it's the difference of the oxygen between the two systems, the arterial system and the venous system. Okay, in other words, during, as you can see in the second dot, during a vigorous exercise, what happens? The active muscle extracts greater amounts of oxygen from the arterial blood and reduces the oxygen content in the venous blood. That's why it happens, and I hope it makes sense. Blood flow, yeah, at rest, you know, not a lot of blood or cardiac output in general, you know, is distributed to skeletal muscle. Why? Because we don't need to. Where is it? anywhere else, brain, um, in our organs, because we may eat or just absorb food. But during exercise, things get different. Most of that, up to 90%, going towards the skeletal muscle, because we need that voluntary contraction, and we need, as we said, oxygen to go there, and all those byproducts to get away from there. Okay. All right. Blood pressure. Blood pressure, the systolic blood pressure, and the systolic again is when the heart contracts, right? Increase. The maximum values, you can see them. Hg is mercury, okay? If the intensity is going up and the SBP is not going up, that's not good. So if we're measuring that and the SBP is decreasing, actually, that's bad. You stop whatever you told them to do, or if you are the person that's happening, you stop exercising, most likely you may need to call an ambulance, as you know. DBP doesn't really change, but we need to terminate exercise if it's above 115. Maximal oxygen consumption. What is VO2 max? We're going to talk about VO2 max. VO2 max is a way, pretty established way to measure our maximal cardiorespiratory fitness. Okay, by measuring our VO2 max, we can use that in order to rank our cardiorespiratory fitness. It's in liters per minute, and it can be relative or absolute. If it's absolute, just a number. If it's relative, it's based on your kilograms, which means on your weight. So for now, just know that if it's we have relative VO2 max, you can compare it between two different people of different body weights because it's per kilogram. The absolute is good, but I mean, if you compare it to yourself and your body weight is the same, the relative is better because it's just per kilo. Okay. Again, not too much information, but enough for now. I hope we're good so far. We're moving to the next system, which is the respiratory system. Okay. Nose, nasal cavity, pharynx, larynx, trachea, and bronchial tree and lungs. Of course, it filters the air and allows for gas exchange with lungs. We have autonomic control structures and we have voluntary control structures. So there are things that we can control and things we cannot control as we're breathing. Okay, I'll explain that in a little bit. If we want to separate it in upper and lower respiratory tract, larynx is where we can just stop. Whatever is above that, including larynx, is the upper, and below that is the lower. Okay, and you can see we have, it can go down all the way to alveoli. We have almost 300 million alveoli in our lungs, and those are important because, as I said before about capillaries, alveoli is where the magic happens when it comes to air. Okay, that's where we exchange the oxygen and we're trying to get rid of byproducts of metabolism like carbon dioxide. Okay, you can see how many times it's broken down once here, and then how many different times it's broken down again and again and again and again and again. And that's why we end up with such a high number of alveoli. Now, the upper respiratory tract, of course, it takes the air and moves into the lower respiratory tract, purifies and humidifies the air. A lot of divisions, generations, as I said, and that's why we have a lot of alveoli. We have trachea and then bronchi, bronchioles, and then alveoli. Okay, all the way down. Again, that's where all the magic happens. And then let's talk a little bit about the ventilatory pump. We have the chest wall, the ventilatory muscles, and the pleural space. So when we talk about the chest wall, we have the intercostal muscles, and then bone-wise, you have the spine, the ribs, and the sternum. Okay. Inspiration, expiration happens if we really think about pressure. Okay. So now you're breathing in, inspiration, and breathing out, expiration, right? Okay. So in order to take air in, we have to have some negative pressure in the pleural space and lungs so that the air comes in. Once they're equal, it stops. And then we'll see how it happens with that elastic recoil of lungs. The air will come out, and that will be a positive pressure, right? And then it stops, and then we go again, and again. Now, when we talk about the respiratory muscles, these are the only skeletal muscles essential to life, and we're talking about muscles that we can control. We have the diaphragm, which is really, really, really important, and then internal, external, intercostals, and the abdominal muscles. So here, this is a rest, okay? This is a rest, and the diaphragm will go down, now create that negative pressure, air will come in, you see the external intercostal muscles, right? And then when it's neutralized, it will stop, air will stop coming in, and then this will recoil, and the what's the word? The diaphragm will go up and will push the air out. That's pretty much it. That's pretty much what I want you to remember for now. Of course, the pulmonary artery supplies blood to the lungs. We talked about that when we talked about the heart. Bronchial artery supply blood to the bronchi and bronchioles. And as I said, that gas exchange happens at the level of alveoli. Now, pulmonary ventilation. So when we are at rest, we are moving 6 liters per minute. When we are at maximum exercise, you see that it's 15 to 25 times more. Wow, right? And lately we think that this happens, we thought it was mostly about oxygen. But now we think that maybe this happens not so much about oxygen, but to offer oxygen, to provide oxygen, but mostly to remove the carbon dioxide. That's very interesting, in my opinion. Think about it. Now, let's talk about adaptations. Of course, lung volume, you can get more air. Diffusion capacity, which has to do with efficiency, how we can move air in the lungs. And maximal ventilatory capacity, the maximum that we can do per minute. And then the submaximal ventilation may decrease, and we think because we don't need, there's not so much lactate to buffer, so there's not so much need for the ventilation to be that high. So it's decreasing. Again, put some emphasis, as you can see. I think it's very interesting to think about. All right, moving along to the energy systems. In general, why do we use food? Why do we eat food? We break it down, we metabolize it because we need energy. Okay, we need energy. I need energy to talk, move my hand. You need energy to watch my video and submit your answers to the LOs. We have 2 types of metabolism. One that requires oxygen, and the one that doesn't require oxygen. So in the presence of oxygen or not in the presence of oxygen. So far, so good? All right. So as you can see here, the main thing that we use for energy is ADP. And if we do something that is more than some seconds, so duration is really important here, right? Okay. So if something, an activity is more than some seconds, like 3-4 seconds, we have some ADP in our body, but that's not enough, which means then we need to create more. The longer the duration, the more we need, so we need different systems. Up to this point, you see it's anaerobic, and now here we talk about aerobic systems. Okay, so based on the exercise duration, we have different types of performance, which means different systems of producing ADP. Again, for movement that lasts longer than a few seconds, ADP must be further manufactured through other means outlined later on as we go in this PowerPoint slideshow. And the relationship between duration and energy sources is right here. Okay. Now, we all have some ADPs in our body, okay, which last for seconds. If we didn't have the capability of producing more, we'll just stop. Like we have batteries and we're in low battery and just there's no more juice and we're done, okay? So in order to produce those ADPs, that energy, the respiratory system and the cardiovascular system play a huge role, okay, with by the oxygen and nutrient delivery and the removal of the waste products. Now, the very first system is the ATP system. Now, we have some ADPs, the energy coins, right? We have some ADPs in our body that are stored and we need to use them. What do we need? We need that energy right here. So we have this thing that called hydrolysis of ADP, which breaks down the ADP through this enzyme to ADP in organic phosphate and energy. Some of that energy will just be released outside body through heat, and some of it will use it. That's what we're looking for. That's why we have this in order to get this, okay? Excuse me. But as I said, we only have a few, some, for seconds, okay? Then we need to create more. So we end up with ADP. What are we gonna do? The very first thing we can do is use creatine phosphate, CP, the creatine phosphate system. Here with the creatine kinase, which is the enzyme, we get ADP, which is really important. So through this, from the ADP, we get the ADP. And of course, we just talked about the hydrolysis of ADP. Why do we use this system? Because it's a rapid system, as you see. One step, that's great. Is it aerobic or anaerobic? Still anaerobic. Anaerobic systems are faster. And that's one of the main reasons our body is designed to use those first. Again, though, we can't produce a lot of ADP. So, based on the duration of the exercise, we may need more. What are we going to do if we need more? We have a third system, which is anaerobic. It's called anaerobic glycolysis. Here, we need carbs. So from a macronutrient perspective, just carbs. Glycogen or glucose. Glucose is the form of the carbs that we have in our bloodstream right now, and we can just break it down and use it. If we don't use it, we can store it. We store it in the form of glycogen. That's all I want you to know for now. Now, that can degrade to pyruvate or lactate. This, although comes from an anaerobic way of producing energy, it could be used later on during aerobic as fuel, anyway, okay? Now we have several steps. We still don't need oxygen. We get more ADPs, but again, several steps. So it's more complicated. That's why it's our third option, okay? Here, it's the fourth option, which is the aerobic system. Acetyl-CoA is very important for you to know for now, and also that we can use all macronutrients, carbs, fats, and protein. Multiple ADPs at the end, but also multiple steps. So it's slow. So if we need something fast and we don't have time, we need to use the other systems first. This is our last option, and we use that if the duration is long enough that none of the other systems produced enough ADPs for us to do. Cool. All right, so here we use all of them. It's called the Krebs cycle. And again, as I said, duration and intensity, of course, increases we go into outlook. All right, oxygen deficit and epoch. Let's talk about epoch a little bit. I'll stop sharing this. I'm gonna talk about epoch, as you can see, is the excess post-exercise oxygen consumption. I'm gonna show you a picture I found online, and I'm gonna try to explain that. I'm gonna stop sharing this. Let me go here. Let me find it. Epoch, excellent. Come back here, share my screen, boom, and boom. There we go. Let's say here you see the duration of the exercise, and here you see the VO2, okay? The oxygen consumption. Now, let's say you put me on a treadmill. You put me on a treadmill, and then this is where you tell me to stop, okay? You take me out of the treadmill. So you're my trainer, tell me to start working out. And in the beginning, I'm using energy that I have stored. So my breathing is really low. I start slowly. At some point, you know, I have a steady pace. My oxygen consumption is steady up here. And then at some point, you tell me to stop. I get off the treadmill, but I'm still breathing heavy. Has that happened to you before? Of course. My question for you is this. Why do I breathe heavy since I'm not doing anything? Let me repeat myself. You told me right here to get off the treadmill. Why am I still breathing heavily if I'm doing nothing, just sitting there? Well, let me answer that question for you. Here, I used some oxygen, some energy, and I created that deficit. Here, I'm trying to replenish that deficit by still trying to get some oxygen in. This is not equal to this, don't get confused. However, this is trying to help me restore this deficit that I had from before, okay? The energy I used without oxygen, I have to give it back now by breathing heavily and restoring. That's what happens. And that's what's called epoch, and that's a very simplistic way to describe it. All right, let me share the PowerPoint slideshow again. All right. Hope it makes sense. Hang in there, moving to the muscular system. Whatever movement we do, like this, requires muscular action. Some action is voluntary, some action is involuntary. When we're talking about the skeletal muscle, the striated muscle, like this, right, it is voluntary. There's neural impulse coming from my brain all the way down. And don't worry, I'm not going to explain it more, like deeper, but it is voluntary. I want this to happen, right? Now my organs move as well. I'm breathing, my heart is beating, I ate something, or I'm drinking water right now. So this water is going to go down my system, right? And it's going to be processed in a way that it's not involuntary. It's going through my internal organs. And then I also, as I said before, I have my cardiac muscle, my heart muscle, which again is involuntary, like it moves involuntarily. Okay, so again, two types of movements that have to do with muscular action, and three different types of muscle. All right, I'll go here. Let's see what's up here, and I'll try to break it down for you. All right, we have a muscle fiber that extends. You see also a Z line here and a Z line here. So if you see it from a lengthwise, Each muscle fiber, we can break it down into the smaller contractile units. That's what we call them. And the term from describe that part from one Z line to the other Z line is sarcomere. So when we put all these sarcomeres next to each other, we have a muscle fiber. And the outside of the muscle fiber is, the outer part is called endomysium. Okay? Inside now the sarcomere of the myosin and the actin, I'm going to come back to that in a little bit. When I have a bundle of muscle fibers on a fascicle, and it's surrounded by the perimysium. And then, if we put a lot of bundles together, we have a whole muscle, and you can see the outside is called epimysium. Okay, and then the muscle, of course, it attaches to the bone through a tendon. We have already covered that. So epimysium, perimysium, endomysium. Muscle fiber, Z to Z line, a sarcomere. Inside the muscle fiber, we have the actin and the myosin. A bundle of muscle fibers is called fascicle. And if we put a lot of fascicles together, we have the muscle we're talking about. Cool? All right. So the sarcomere, as I said, is the smallest contractile unit of the muscle. And it has the actin and the myosin. The actin is the thin filament. The myosin is the thick filament that has the cross bridges. The actin, it can be broken down in the troponin and the tropomyosin. Okay? Well, let me talk a little bit about the sliding filament theory and then about the all or none principle. Let's take the bicep. Actin, thin, myosin, thick with cross bridges. Okay? Here, relaxed. Here, we have contraction. Okay? So if you see this, it's the same line, but here, when the muscle contracts, you can see this difference from here to here, right? So it becomes smaller, it contracts. The length is becomes smaller. And that's why we said a couple weeks ago that the muscles pull, right? So they pull, the cross bridges are going to attach to the actin, and the myosin will pull the actin together closer, and that's why it's contracted, and that's why that length is smaller than this length. Yes? So the more sarcomeres are going to get contracted, the smaller the muscle will end looking. Sarcomere from here to here. The more sarcomeres are going to get contracted, the smaller the length of the muscle. Make sense? Also, the thick is pulling the thin closer. That's why from this relaxed length, we go to this contracted length, shorter. I hope you got it. Okay. And in the same sarcomere, all the myosins and all the actins are going to contract. It's not some of them. What kind of contractions can we have? We can have isometric, static, right? It's like you're doing a plank, you're doing a wall sit, or anything. Like you just grab two dumbbells and you do a lateral raise and you just stay there. Just stay there. What's the key term here? Length. The length of the muscle doesn't change. You contract it and you stop. It doesn't change. So it's isometric, it's static. It's static. Okay? Very beneficial for rehabilitation and for specific reasons. We're not going to go into detail right now. Dynamic isotonic is what we usually do. the muscle shortens, the muscle lengthens. Okay, we have concentric, eccentric contraction. When the muscle shortens, the bicep, concentric. When the muscle lengthens, eccentric. You have to know that. Eccentric contraction, although it may appear weird to you right now, it can produce more force than this way. That's why a lot of times we're doing negatives. Again, I'm not going to go into detail. We talked about negatives a couple of weeks ago, I think, or last week. And then isokinetic, it's very rare. You need specific machines like pneumatics and stuff like that. They maintain the same speed of the muscle contraction. Okay. Dynamic, static. You know the difference? No concentric, no eccentric. You have to know those terms and what they mean, please. All right, muscle fiber types. We have all in the same muscle. We have all muscle fiber types. Okay, and that's why we can do a variety of activities based on the needs we have. That will make sense in a little bit. Oh, and we're still looking, there's a debate about if muscle types can change based on training. I'll just say a couple of things in a sec. So we have the type 1 and we have the type 2. There are more types pretty much. You see type A or type B or type X. But in general, let's say we still, for educational reasons, at least we have type 1 and type 2. Type 1, aerobic endurance activities, right? Like a marathon runner, you would expect them to have more type 1 than type 2, right? They have a high resistance to fatigue, of course, but they cannot produce a lot of power. And this is kind of the opposite, especially 2X, right? A lot of force, but not high resistance to fatigue. They get tired easily. Okay, so sprinter will have a higher percentage of type 2X, especially muscle fibers, than type 1. Now, type 2A is something interesting, something in between. And we know that sometimes with a lot of aerobic training, they can be modified a little bit towards more type 1-ish muscle fibers. All right. PED212. I can remember the number right now, but 315. But the analyzing human movement, we're talking about neuromuscular activation a lot in sports neuroscience. So that's just an introduction of the introduction. Okay, so for activation, in order for a muscle to move, we need the neurons to pretty much communicate that from our brain. Okay, so that's why we talk about neuromuscular activation. We'll have the brain, and I added that picture over there so it makes sense. The brainstem goes away to the spinal cord, and then it attaches to a specific motor unit. That motor unit, is attached to specific muscle fibers, and that's how it happens. Now, motor unit, it has the motor neuron and all the muscle fibers that it innervates. Now, you need to know at this point that a motor unit will innervate muscle fibers of the same type. Remember that. Another motor unit will innervate muscle fibers of a different type in the same muscle, but motor unit innervates muscle fibers of the same type. That's what you should know at this point. Now, if you lift heavy, that affects the amount of motor units that are going to get activated and the frequency. How many times the same unit is going to fire? Just once and just relax? once, and then again, 3 times, 4 times, how many times? So that depends on how heavy we're lifting, for example. The skeletal system, we have already covered it. I'm not going to go over that. The joints, we have already covered them. I hope you remember what anchors the ligaments, what connects a bone to a bone, and what connects the muscle to a bone. Proprioception. It's a very cool word. We hear that all the time, and for now, just know that is for us to. It's information that we're receiving from our periphery, and we understand where our body's located. Okay, and if there's a specific movement of a limb or something, we have a sense of it, and we know what it is in space. Okay, that includes range of motion. We have active range of motion, passive range of motion. Of course, passive range of motion, if they also does it on us, will be greater than active. Neurological system. Again, there are other courses for this, but we have the CNS, which is the brain and the spinal cord, and the rest is the PNS. Now, the CNS, as I said, is the brain, which is protected by our skull, and the spinal cord, which is an extension of the brain, and then it goes out to the periphery, which is the PNS. Cranial nerves associated with brain, the spinal cord, and then we have ganglia, which is a group of nerve cell bodies. In general, 2 types of nerve fiber types, nerve fibers, afferent, efferent. I have a picture later on that's not in the book just to explain that. Afferent coming towards our brain, spinal cord and brain, efferent coming down the other way, okay? Now, the PNS is broken down into the somatic and the visceral. Look. Now, this picture is not in the book. I added it there just to explain. All the way up. First of all, you can see by the different colors we have CNS, PNS, okay? Distinguished by the difference of colors right here. Now, let's talk about the afferent. We have stimuli that comes from, let's say, our organs and from our periphery in general, right? Senses like I'm touching now my face. There's information coming down, it comes all the way to my brain about temperature. If there is pain, I'm touching my face, right? So that's sensory stimuli. And that's the afferent division that takes that information and brings it to the spinal cord and if necessary to the brain. And from there, we'll have the efferent, it comes the other way down, and it can be somatic or autonomic. Let's talk about somatic. Somatic has to do with motor neurons, skeletal muscles, voluntary action. Okay? Like moving this. Maybe there's pain, so I'm just move it away. Now I have the autonomic nervous system. I can break it down into sympathetic and parasympathetic. Sympathetic has to do with alarm conditions. So like somebody scares me, I'm screaming, or like my testosterone, adrenaline goes up, which means my heart rate goes going up, and I'm going into an alarm condition. Stressful. It's stressful. And then we have the parasympathetic nervous system that's like, it's cool, bro. Relax. It was just a joke. Chill. Right? And tries to take my heart rate down, put me back in that homeostasis. Right? So, involuntary action. I don't control it pretty much. Right? But that's called parasympathetic. So again, afferent, somatic, pretty straightforward, and then the autonomic, we have the sympathetic and the parasympathetic. Cool? I hope it's cool. Cool. All right. Yeah. Let me talk about the size principle. It has to do with your second law. Let's talk about thresholds. A motor neuron, different motor neurons, different recruitment thresholds. If, let's use an example, like lifting. Use really lightweight. I'm gonna have to recruit the ones that have really low threshold. As I'm increasing the weight, I have to keep adding, right, motor units that have higher threshold. If I put my maximal weight, which motor units am I gonna activate? That's the question for your LO. Think about thresholds. Think about keep adding. What's gonna happen at the very end? Proprioceptors, again, we'll have different courses for that, but I want you to know two things. Proprioceptors are giving us information from the periphery towards the brain. The most important ones that we're going to talk about are the muscle spindles and the Golgi tendon organ, GDOs. Big difference. This is in the muscle fiber. This is in the tendon. This, if you think about the movement at that muscle, if it detects some kind of movement under specific conditions, it will try to stop that kind of movement. This will try to facilitate it. Example, if I come and grab you from the hand and pull you, what are you going to do? You're going to pull the other way around. That's a reflex. How is that happening? Well, the muscle spindles are very sensitive, and they understand that not only the muscle is stretching as I'm pulling, your body's stretching too fast, and trying to protect you, you react by pulling the other way. Here, the GDOs, they understand that there's no kind of danger. It's like when you're stretching, like static stretching. After a while, we usually say, 20, 30 seconds, the muscle relaxes and you can stretch more. That's because the GDOs are. That's all I want you to know for them. Overload principle. What's happening with resistance training? Improve aerobic enzymes. Of course, we have more neuromuscular coordination. And basically, in the beginning, those gains in the first weeks is not happening because you become stronger. It's happening like the first 3-4 weeks because of the neuromuscular coordination. Those are nervous gains, mainly. They're not muscular gains, but because the nervous system has to coordinate with the muscular system in order to have that voluntary action, muscular action, it looks like you're becoming stronger. No, you're not. Not even your trainee becomes stronger. They feel it, but it's nervous, and there's gains in the nervous system more than in the muscular system. Does that make sense? Now, overload principle. We talked about exercise and stress. If you keep lifting 5 pounds, what's going to happen? You're going to adjust, and then you're going to stop adjusting. There's not going to be any kind of hypertrophy, for example. But if you have some progressive overload, which means more sets, more reps, or more weight, or less rest, something that changes, like you have to manipulate the variable, then you go according to the overload principle. You change the stress, you increase the stress in a way because you're ready to move up, and that's how there's progress. Okay. What happens with cardiovascular exercise training? Functional capacity. Okay, there's a more efficient. Increase, of course, aerobic capacity or VO2 max if you want to measure it that way. Reduce heart rate, systolic pressure at rest, and of course decrease lactic acid production and muscle blood flow. Resting heart rate decreases. We know that fit people have lower resting heart rates. Stroke volume increases at rest and during exercise. It will increase during exercise. The difference will increase between the arterial system and the venous system. Resting SBP and DP may decrease and less lactic acid will be produced at sub-maximal workloads. Again, a little more efficient. You can see the table here. What else? Yeah, sex-specific improvement. Women respond the same way, okay, well, for the most part. But the older you are, the less improvement you see. The less physically active you are, the more improvement you'll see. And the less your initial VO2 max is, the more improvement you'll see. I hope it makes sense. Now, the more frequent you exercise, the more intensity you use, and the more duration you use, of course, the more improvement you'll see. Okay. And when we talk about exercise prescription, cardiovascular, or any kind of type of exercise, you'll see that in more depth. Improvements in so many areas, right? Cardiorespiratory function, immune function, decreased risk of all those, mortality and morbidity, and even, the blood lipid profile, triglycerides, and cholesterol, and so on and so forth. Lipemia. We're going to talk about things like that later on. I don't want to. I don't want to keep you more, and I don't want you to freak out even more right now because I know I covered a lot. Okay, take home points. Let's see. You have now been introduced to the basic concepts of exercise physiology, including cardiovascular and pulmonary physiology, musculoskeletal function, and adaptations to training. However, endocrine, metabolic, and other body functions are also important. Thus, it is recommended that as new issues with individual clients arise, personal trainers should seek out additional references that can assist in understanding the conditions and how the body functions under conditions of physical stress. This proactive approach to learning a client's condition will assist the PT to develop safe and effective exercise program for their clients. All right, guys. That's all. I hope it wasn't too much. Take it easy. Have a great week. And in the meantime, lift intentionally, not habitually.